Okay, good evening to everyone present here. So the topic of I am Vishal Dhar, a PhD scholar from the Department of Chemical Engineering, IIT Guwahati. The topic of my presentation is viscoelastic and flow properties of CO2 foam stabilized by surfactant nanoparticle systems. I am working under the supervision of Professor Pankaj Tiwari and Professor Subrata Kumar Majumdar. This is the outline of my presentation: introduction, materials and methods, rheology study, conclusion, and references. So before going to the presentation, here is a brief introduction about my campus, IIT Guwahati. It is the sixth member of IIT fraternity. It was established in 1994. It is ranked 32 globally in research citation per faculty category by QS World University Ranking 2024. It retained the seventh position among the best engineering institutes of the country in NIRF ranking 2024. It is ranked second in India in petroleum engineering and 50 to 70 globally according to 2024 QS World University ranking. It is ranked second in Swachhata ranking by Government of India. Also, IIT Guwahati ranks sixth globally in Sustainable Development Goal 7 by Times Higher Education Impact Rankings. So coming to my work, the energy around the world is divided into three main parts: the fossil fuels, the renewables, and the nuclear. The fossil fuels comprises of about 78% of the energies, and which can be divided into coal, oil, and natural gas. According to International Energy Outlook 2017, it predicts that the global energy consumption will rise from 28% between 2015 to 2040. To combat this energy demand, we need to produce the oil that is found in the reservoir. The different mechanisms are the primary recovery, which is mainly natural flow and artificial lift. Process involved The process involved are expansion of dissolved gases, rock and fluid expansion, aquifer influx, and gravity. Next is secondary recovery, which mainly comprises of water flood and gas injection, and the main mechanism is pressure maintenance. Then tertiary recovery, the main processes are IFT reduction, viscosity reduction, and wettability reversal. The different types of tertiary recovery that are used worldwide are thermal, which includes the steam injection and hot water injection. Then there is gas flooding, which includes hydrogen flooding, flue gas flooding, and CO2 gas flooding. Then there is chemical and other technologies, which includes polymer, alkaline, and microbial. The different recovery factor for each of these are: for the primary recovery, the recovery percent is 5 to 20%. For secondary, it is 20 to 40%. And for EOR, enhanced oil recovery, it is 30 to 60%. The recovery efficiency can be calculated by multiplying volumetric sweep efficiency with the displacement efficiency. The formula for that is shown in the presentation. The factors that affect the residual oil saturation are mainly capillary number. This acts at the microscopic level. Then there is mobility ratio that acts at the macroscopic level. The formulas for both these type of recoveries are shown in the presentation. For CO2 flooding principle, it can be divided into miscible flooding and immiscible flooding. Miscible flooding is a technology which operates above the minimum miscibility pressure, and immiscible flooding, it operates below the minimum miscibility pressure. Miscibility pressure can be described as the pressure is the least pressure at which the gas that we have injected into the reservoir gets completely miscible with the crude oil that is already present in the reservoir. The different mechanisms involved in miscible flooding are vaporizing gas drive, mobilization of lighter crude oil components, reduction of oil viscosity, and swelling of oil, also ultra low IFT. And in immiscible flooding, there is solution gas drive, reduction of oil viscosity, swelling of oil, and low IFT. So in normal CO2 flooding, that is immiscible CO2 flooding, we inject CO2 gas into the reservoir, which is followed by water drive. But there are different problems that affect the CO2 flooding, that is viscous fingering, mainly caused by mobility control. Then there is loss of miscibility. Then there is gravity of override because of the density difference. To combat this, we shift to water alternating gas flooding, in which CO2 and water gas water is CO2 gas and water are all injected alternately. But this also leaves a huge chunk of crude oil in the reservoir, because CO2 gas has a very lower density than crude oil and is not able to push the crude oil through the reservoir. To mitigate this, we shift to surfactant or alternating gas flooding. This can be also called foam flooding. Foam in such cases have higher density than CO2 gas and has a better viscosity, which helps the mobility of the CO2 foam in the reservoir. A CO2, here I have shown a foam structure. You can see the gas phase. In our case, it will be CO2 gas. It is the different gas phases are separated by a liquid film, that is the lamellae. Moving on, in our study, the materials and method part, the surfactant that we have used in our study is alkyl polyglycoside. It is a non-ionic biodegradable green surfactant. These surfactants are less toxic and highly biodegradable, making them comparatively safe and environment friendly. Foam generated using APJ surfactants are resistant to high temperature and high salinity. We have found the CMC of the surfactant. CMC, it is the concentration of surfactant in a solution above which missiles form. Surfactant in a solution lower the surface tension by absorbing at the surface below the CMC. Most additional surfactant after CMC are they form missiles. So the for the APG surfactant, the CMC was found to be 0.38%. Then we have used different types of nanoparticles in our study. The nanoparticles that we have used are silicon oxide, titanium oxide, and aluminum oxide. Nanoparticles, they have become very popular in terms of increasing the stability of CO2 foam under harsh reservoir conditions because of their remarkable stability and excellent surface properties. After mixing the surfactant with the alkyl polyglycoside, we have again found the CMC, and we have seen that for the uh, silicon oxide and for the aluminum oxide, for the silicon oxide and the titanium oxide, the CMC remains the same, that is 0.3%, and for aluminum oxide, the CMC shifts to 0.48%. This is our foam analyzer setup that we have developed in lab. This is our foam analyzer where we can generate the foam, and after that I have bottled the foams in different measuring cylinders. We have used different types of chemicals and different types of surfactants and nanoparticles to generate different foams. After that, we went for the viscosity study. First, we have studied the viscosity of the surfactant, only the surfactant solution. The viscosity of the FPG CO2 foam solution decreased with increasing shear rate, confirming a shear thinning behavior. At 1 per second, the viscosity ranged from 26 to 135 centipoise depending on concentration, whereas at 100 per second, it stabilized between 4 to 10 centipoise. The increase in concentration from 0.1 to 0.58% led to higher viscosity plateaus at high shear rate, indicating stronger micellar structural interactions. After that, we have used the 0.38% APG solution to mix, and we have mixed it with different. We have used three different types of APG concentration, that is 0.28% APG, 0.38%, and 0.48%, and we have mixed with different nanoparticle solution. First, we have used the silicon oxide nanoparticle. Here we have also seen the same shear thinning behavior is shown by the mixture of surfactant and nanoparticle. Increasing the nanoparticle concentration raises low shear viscosity and enhances shear thinning. 0.58% silicon oxide consistently shows the highest viscosity, while 0.18% silicon oxide constantly showed the lowest viscosity across with all the APG concentration. Addition of silicon oxide nanoparticles clearly tunes viscosity without excessive thinning, giving good control over foam and dispersion stability. Next, we have used the same method for the other two nanoparticles, that is aluminum oxide and titanium oxide. Similar trends have been seen for aluminum oxide and titanium oxide. 0.5 weight% consistently showed the highest viscosity, and 0.1 weight% showed lowest viscosity. The viscosity shear rate profile of 0.3 weight% APG showed valence rheology, moderate viscosity at low shear, stable shear thinning, and predictable flow behavior, making it ideal for further optimization. For our rheology study, we have taken the 0.3 weight% surfactant solution and mixed it with different surfactants. First, we have used the silicon oxide. The observations were we have used for the rheology study, we have used the strain percent from 0.001 to 1000 strain percent and find the LVR region. LVR region is the region where the foam acts as a elastic fluid, that is, the foam structure is not deformed. The storage modulus G dash and the loss modulus G double dash, which the storage modulus, it represents the solid like behavior, and the loss modulus, it represents the viscosity behavior, viscous behavior or liquid like behavior, where where shown in the graphs. The increasing nanoparticle concentration pushes the crossover of the storage modulus and loss modulus points to higher strains or stresses till 0.38% silicon dioxide and then decreases, which means that 0.38% silicon dioxide generates more stable foam than other concentration of silicon oxide. Same is the case of aluminum oxide. The 0.3 weight% aluminum oxide created more stable foam than other concentration. But in case of aluminum oxide, we have seen that the gap between the storage modulus and the loss modulus was less, which indicates that the foam follow the elastic and the viscous behavior strongly throughout the strain range. Next, for the titanium oxide nanoparticle, similar relations have been seen, and the increasing the concentration of the titanium oxide pushes the crossover of loss modulus and storage modulus to higher strains or stresses till 0.38% concentration and then again decreases. Next, we shift to the microscopic study. From here, we can see the different microscopic images that we have taken at 0 minute, then 30 minute, 60 minute, 90 minute, and 120 minute. First, we have seen for different silicon oxide nanoparticle or different concentrations of silicon oxide nanoparticle. Here also 0.3 weight% alkyl polyglycoside was selected for the microscopic study. The image of 0.3 weight% silicon oxide showed better stability than other nanoparticle, because you can see from the pictures that at 120 minutes also the foam is much stable than other concentrations of silicon oxide at 120 minute. With time the gas bubble size increased because the gas bubbles coalesced and formed bigger bubbles, and the lamella size decreased with time. Similar observations were seen for the aluminum oxide, with 0.3 weight% aluminum oxide giving better stability than other nanoparticle concentration. And also for titanium oxide, similar images have been captured, but here the 0.28% and 0.4 weight% also showed very good results, but the best result was shown only by 0.3 weight% titanium oxide nanoparticle. So to conclude my study, these are the points. The alkyl polyglycoside, a natural surfactant, and 3 nanoparticles, silicon oxide, aluminum oxide, and titanium oxide, were selected for the study. The compounds were used to generate CO2 foam. CMC of alkyl polyglycoside was found to be 0.3 weight%. The CMC remained same when mixed with silicon oxide and aluminum oxide nanoparticle, but changed to 0.4 weight% when it was mixed with titanium oxide nanoparticle. The viscosity study showed shear thinning behavior with 0.3 weight% APG, demonstrating most balanced rheology parameter among all the CO2 foam formulation. The viscosity increased with increasing concentration of the nanoparticle for all the 3 types of nanoparticles. The viscoelastic study showed LVR region between 0.001 to 100 strain%. Increasing nanoparticle concentration pushes the loss modulus and storage modulus crossover point to higher strain or stresses value till 0.38% concentration, and then decreases for all the nanoparticle used. 0.38% alkyl polyglycoside was selected for microscopic study of CO2 foam. The images for 0.38% nanoparticle combined with 0.38% alkyl polyglycoside showed better stability than other nanoparticle concentration, and that was true for all three types of nanoparticles that were used in the study. These were the references for our study. I want to thank the Ministry of Education, Government of India for providing the funding through PMRF scheme. I also want to thank Department of Chemical Engineering, IIT Guwahati for providing all the necessary facilities. The Central Instrument Facility of IIT Guwahati. I want to thank Professor Pankaj Tiwari and Professor Subroto Kumar Majumdar for their generous support, motivation and suggestion throughout the work, and also to the GOPE organizer for providing the opportunity to present my work. Thank you.